Hello everyone, I'm Hamad Awad, a graduate student in cybersecurity at Georgia Tech, and I'll be presenting a research paper titled Volttack: Control IoT Devices by Manipulating Power Supply Voltage for the ECE 8813 Cyber Physical Systems Security course for the spring 2025 semester. Before we dive in, I would like to acknowledge the authors of this paper and the institutions supporting their research. This paper was written by Kai Wang, Xiling Zhao, Xiao Ji, Xin Yan, and Wenyan Xu at USS Lab in Zhongyang University, and Xiaohou Li at Hikvision Digital Technology. Their work is a significant contribution to the field of cybersecurity, especially in the domain of embedded and cyber-physical systems. This paper was presented at the 23rd IEEE Symposium on Security and Privacy in Auckland 2024, and the research is published in IEEE, and you can access the full paper at the provided link. The study builds upon previous research in side channel attacks and power supply security, but introduces a fresh and alarming perspective. The presentation is structured as follows: an overview, the problem statement, background, threat model, effect on electronic components, controlling sensors and actuators, an evaluation, discussion, related work, and finally a conclusion. This paper discusses a new type of attack on IoT devices called Volttack. The attack exploits vulnerabilities in power supply modules by injecting malicious signals into them. These disturbances cause sensors and actuators to behave unpredictably, which can have serious real-world consequences. The study provides experimental validation using real IoT devices and proposes security improvements to mitigate this threat. Unlike conventional cyber attacks that rely on malware or software vulnerabilities, Volttack exploits the physical layer, specifically the way electronic devices handle power fluctuations. This makes it a low-cost, highly effective, and difficult to detect attack method. Understanding Volttack is crucial because IoT devices are widely used in critical infrastructure, including medical devices, smart homes, industrial control systems, and autonomous vehicles. So, this paper aims to improve the security of power supply modules to mitigate these attacks. The primary issue explored in this research is the lack of security measures against high-frequency power supply attacks. Specifically, current power supply testing covers signals in the 150 kHz to 80 MHz range. However, Volttack operates between 80 MHz and 500 MHz, meaning current protections fail to block these high-frequency signals. This attack can alter sensor readings and actuator behavior, leading to critical safety issues, such as a force sensor DYTB-002 that is used to measure of the force pressure of a driver into the brake pedal. If we inject a signal of 1 volts at a frequency of 342 MHz to the 24 volts operating voltage, it can decrease the sensor reading and can cause the braking distance to be doubled. Another example, a temperature sensor, DHT11, that is used to measure industrial environment temperature. If we inject a signal of 0.5 volts at a frequency of 121 MHz to the 12 volts operating voltage, it can increase the sensor output by 139 degrees Celsius, which may lead to false excess cooling, which caused a British die factory explosion. A servo motor that is used to control the joint rotation of robotic arms. If we inject a signal of 1.3 volts at a frequency of 340 MHz to the 5.5 volts operating voltage, it can rotate the joint by 58.4 degrees clockwise, which might injure the user. A valve that is used to in the flow control of natural gas. If we inject a signal of 0.5 volts at the frequency of 75 MHz to the 5 volts operating voltage, it can open the closed valve to 34%, which might cause a gas leak. So, by targeting power supply, attackers can gain indirect control over sensors, outputs, and actuator inputs, effectively manipulating device behavior without hacking software or bypassing encryption. And the examples mentioned show us how dangerous such an attack can be. The Internet of Things, IoT, consists of interconnected physical objects communicating over the Internet. These devices rely on 3 key components: the power supply, which provides electricity to the device, sensors that measure environmental data, and actuators that perform physical actions. The power supply rejection ratio, PSRR, measures a power supply's ability to reject noise. If compromised, IoT devices become vulnerable. Traditionally, cybersecurity research focuses on software vulnerabilities, such as buffer overflows, malware, and firmware exploits. However, Volttack operates at the intersection of hardware and power electronics, which has been largely overlooked in security discussions. The attacker needs access to the power supply in order to inject malicious signals. Two possible attack methods are direct interference with the input power signal or manipulating the internal components to alter behavior and change the input-output relationship. The attacker must know the target device model and obtain an identical one in order to study its vulnerabilities before launching the attack and predict its output. Attacks can be carried out physically or remotely via a compromised power delivery system that includes a wireless connection, such as Wi-Fi or Bluetooth module. This means that potential attack vectors could include smart power grids, malicious third-party power adapters, or even power line communication networks. Electronic components are highly sensitive to frequency variations. High-frequency signals can bypass protective filters, disrupting sensors and actuators. For example, in this given equation, I out is the output current and VCC is the input voltage, while F is the frequency. So, from the equation, we can see that a higher frequency gives a higher input-to-output gain. These adjacent graphs represent the input frequencies of two sensors and the effect it has on the input-to-output gain. In the first graph, power supply signals in the range of 10 MHz to 130 MHz can go through the filter, but there is a positive gain at 110 MHz, which the noise is amplified. So at 110 MHz, a Volttack attack can be triggered. In the second graph, in the range of 10 MHz to 500 MHz, different attack signals at certain frequencies can bypass the filter and have a positive gain. Since different devices react differently, an attacker needs prior knowledge to optimize their attack. This is particularly dangerous in safety-critical applications, such as medical devices, autonomous vehicles, and industrial automation. An attacker can predict and control sensor readings or actuator movements by testing the attack on the same model of the victim's device. As the diagram shows, the attacker changes the compensation signal by the power supply noise, which results in a manipulated output. As an example, if a temperature sensor is manipulated, an industrial cooling system could overcompensate, leading to energy waste or equipment failure. Or, if a robotic arm's motors are manipulated, it could perform unintended actions, posing serious safety risks. So, just imagine how dangerous the consequences of manipulating sensors in aircraft or tampering with fire detection systems in smart buildings. The researchers tested Volttack to evaluate it in real-world scenarios using 6 different sensors and 3 actuators, like force sensors, electric valves, and a robotic arm. They also showed different attack scenarios that can be used in real life by attackers, like an exposed IoT device, employees conducting the attack, or unauthorized access to a device or facility. They demonstrated 3 different attack vectors. First, a counterfeit battery that works as a normal battery but has a signal generator connected to a Wi-Fi module inside it, which an attacker uses to trigger the signal manipulation. A current injection probe by injecting a wire to the target device and connecting it to the signal generator. And the third attack vector is a customized coupler which generates an electromagnetic field and induces current through a wire. In order to have a successful Volttack attack, the attacker must prepare well by studying the target device, determining the optimal attack signal, and finding a suitable delivery method. However, different countermeasures can be used to place in order to defend against Volttack, such as monitoring power supply voltage for anomalies and improving the noise rejection performance, which costs about $2 per device. Similar related work focuses on digital circuits by using voltage manipulation to extract keys and bypass authentication, and analog circuits such as power disturbances in sensors and IoT devices, and the effect of signal interference and fault readings and control. While Volttack itself also focuses on analog circuits, it exploits power vulnerabilities to manipulate sensors and actuator outputs, and it focuses on analog without firmware compromise. In conclusion, this paper reveals a power supply vulnerability that enables manipulation of IoT sensors and actuators. Through analysis and experimentation, it demonstrates and evaluates Volttack, an attack that alters device behavior using power injection, and explores potential countermeasures. Thank you for your attention, and if you have any question, please feel free to post them on Add Discussions. Thank you.